Okay, good morning. Welcome to the seminar today. It's my great pleasure to have Jinmin Yi as our speaker today. Jinmin just got his PhD degree in physics from Perimeter and the University of Waterloo. Uh, I overlapped with Jinmin at Perimeter for multiple years, and have had the privilege to have written, I think so far, three papers with Jinmin. Of course, Jinmin is very productive during his PhD study. And his work during PhD already ranges from wire semi-metal to quantum information, quantum complexity, approximate error correction, and to quantum many-body entanglement, topological phases, this and that. Sometimes I feel Jimmy is a magician in all kinds of technical tools. Uh, in particular, a lot of non-standard, unfamiliar tools to many of us. I think today we will also learn something very interesting. Jimmy, please go ahead.
Thank you so much, Nugent, for your kind words, and it's my great pleasure to be here um, to talk about the other-disorder trade-off in dirty quantum systems. This is a joint work with Professor Chong Wang from Perimeter Institute, and it's based on this work on archive from 3 months ago. So let me begin the talk by briefly talk about the canonical example of the transverse field Ising model, which has a phase diagram of both the order and disorder phases. So the Hamiltonian is like this, and um, you can just tune the transverse magnetic field edge, and when edge is small enough, the system will be in an order phase. When edge is large enough, the system will be in a disorder phase. So um, one thing to emphasize is just that in the order phase, the phase can be perfectly captured by the non-range two-point coordinators of GIGJ, and as long as there is spontaneous symmetry breaking of this asymmetry, these two-point coordinators will always be non-zero. On the other hand, if you consider large enough edge and the system is in disorder phase, the phase can be actually captured by non-symmetry strings. For example, here from side I to side J. And as long as the system is disordered, you will find out that this restricted symmetry operation will have a non-zero expectation value. So by thinking about the Kramers-Wiener duality, we will be able to know that as long as your system is away from criticality, this order parameter and the disorder parameter are mapped into each other, and so that we know that these are perfect diagnoses of the two phases, and you always have exactly one of them survive. Uh, by the way, please interrupt me whenever you have any questions. So the trade-off or the the behavior of the order and disorder parameter is actually general. It goes beyond the transverse field Ising model. In fact, if you consider any clean system with Ising symmetries, you can always define the order and disorder parameters as in here. For the order parameters, we say that a system have an order parameter OI and OJ if there exist two operators OI and OJ near the site I and site J. Both of them are odd under the Ising symmetry, and they have non-range coordinators, even when I and J are very far from each other. On the other hand, we say that a system will have a disorder parameter O and OJ if similarly we have two operators localized near site I and site J, but the addressed restricted symmetry operation with the operator O and OJ has a non-zero expectation value, even if I and J are very far away from each other. So empirically, people already know that this order and disorder parameter serves as very powerful tools of understanding symmetry breaking and symmetric disorder phase. But Nevin has this great work where he proved rigorously such that this kind of trade-off or this kind of usefulness of the order and disorder parameters in detecting phases. It's actually rigorous. More explicitly, it shows that if you consider a translation invariant spin chain and which is gapped in every symmetry sector, it must have exactly one of them. So you either have the order parameter to be non-zero or the disorder parameter to be non-zero. Moreover, we know that the disorder parameter, if that survives, will have an even endpoint. So any disorder parameters will have an even OI and OJ under the Ising symmetry.
Jimmy, if
Sure.
for the disorder parameter, if the endpoints are odd, what happens?
Um, you can actually show that this is impossible in a translation invariant spin chain. Uh,
Having non-range order is impossible.
sorry?
Having non-range disorder is impossible. What is impossible?
Oh, so non-range disorder is possible, but if you consider a non-range disorder, a disorder phase, you'll find out that the OI and OJ must be parity odd under the Ising symmetry. If you consider some parity, parity even under the Ising symmetry. If you consider some parity odd operators, then this expectation value will still go to zero.
And this is related to the absence of non-trivial SPT with Z2 symmetry.
Yeah, exactly. Uh, if you consider Z2 times Z2, of course, you will have odd endpoint, and I will go there like in near the end of this talk.
Mhm.
Yeah, so here in most part of the talk, we will only focus on like Z2 symmetry, like a single Z2 symmetry. So you will only have even endpoints. So what I want to emphasize is just that these two parameters are very helpful. The order parameter can help you to detect spontaneous symmetry breaking. The disorder parameters can help you to detect SPTs. So, um, however, in real materials, we know that we don't actually have clean materials. There will also always be like quantity disorders, imperfections, this and that. So it's natural to ask whether this kind of probes will also be useful in dirty systems where we have quantity disorders. So here's the main result of this talk. We actually show that these two parameters are still very useful in quantity disorder systems. More explicitly, we show that if we consider a gapped ensemble, which I will define later in this talk, with exact Z2 symmetries and average translational symmetry, and the with a quantity disorder so that the disorder potential is short-range correlated, then all of our previously discussed probe still works. We show that there must exist exactly one of the following. We either have an O1 order parameters or an O1 disorder parameter with even endpoints. We also show that while the real-region effects, the Griffiths type real-region effects are very important in disorder systems and sometimes can ruin a lot of naively expected mean field network results. Our results, and especially the dichotomy and the trade-off between the order and disorder parameters will still survive, even if you consider the real-region effects. We also show that our results can have a lot of applications in different kind of disorder systems. We show that the idea of the string order parameters or the idea of order parameters will still work well, even if you consider dirty Z2 times Z2 SPT. We also show that our results can give you an LSM type constraint for dirty systems with with symmetries that have projective representations on each side. Our results can also be generalized to fermionic chains where we show that similar um, trade-off still holds. It's just that instead of a trade-off between order and disorder parameter, we now have a trade-off between different kind of string order parameters. So here's the outline of the talk. First of all, I will talk about our main results. I will tell you the order and disorder trade-off theorems. I'll give you some intuitions and then sketch the proof. Then I'll briefly talk about how we can incorporate real-region effects. Then I will end the talk with applications to both SPTs, LSM, and fermionic chains. Let's first talk about the main theorem. To get some idea of how this main theorem can work, let's look at some simple examples where we have we start with the transverse field Ising model and we add some randomness to the system. The first naive thing that you can do to deal with the transverse field Ising model is just to change the ZZ coupling to a random coupling with sign fluctuations, just like this. And in this case, if the transverse field H is small enough, we still expect that for any disordered realizations, the system will still be ordered or have SSB. In this case, if we consider any single disordered realization omega, the two-point coordinator Cij will still be O1 for any separations between I and J. It's just that it will also depend on the sign of the ZZ coupling. However, since we know that the sign of the Z coupling can just fluctuate freely, we know that if we take the expectation value of the two-point coordinators, it will just go to zero. So the naive way of taking the expectation value will not give you any other parameters. On the other hand, since we know that all that matters is just this sign, we can just naively take the absolute value and then take the disorder average, and we'll find out that this kind of Edwards-Anderson type coordinator will give you an O1 result.
Sorry, Jinmin, can I
Sure.
ask a question here? You mentioned you need some translation, average translation symmetry.
Exactly.
What is the here?
The average translation symmetry just tells you that if you apply a translation to the probability distribution of the disorder potential, you will get exactly the same disorder probability distribution. So now here, all of these random couplings are just independent. So on every side, you have either plus or minus. So if you apply a translational symmetry to that, the new disorder the new probability distribution will also have both plus or minus, so it doesn't really change anything. That's the
Okay,
average
so
translation
so
symmetry.
so that means under the ensemble average, for any observable, actually you get the same
Yeah,
result
exactly.
under translation.
Yeah, exactly.
I
If
see.
you
I see.
consider naive expectation values, or you consider this kind of absolute values and average, you will always get like translation invariant result.
Okay, thank you, thank you.
Yeah. So another example that you can think about is just the transverse field Ising, but you add the randomness to the transverse field. In this case, if the magnetic field is large enough, we will still expect that for every disorder realization, the system will still be in a disorder phase. So if you consider this string order parameters, you take the expectation value, it should still be non-zero. It's just that it depends on the sign of every transverse field. So just like the previous example, if you just take the naive expectation value or disorder average, you will just get zero. But if you take the absolute value first, you will also get a O1, uh, O1 expectation value. So this just tells us that um, while while if you take the expression value naively, you don't get any useful information. As long as you take the magnitude first before the averaging, it just perfectly captures all the physics right around here. So this motivates us to our definition of order and disorder parameters um, in the disorder ensemble. So for the order parameters, we say that for any side I and side j, there exists an order parameter OI and OJ, as long as just like before. OI and OJ are odd under the Ising symmetry, and the expectation value of the absolute value is larger than some constant. Similarly, we can define the disorder parameters. The only difference is just that we add a symmetry string between the side I and side j. And the difference here is just that the OI, a priori, we don't know about the parity of OI and OJ for the disorder parameters. So if OI is even under the symmetry, Ising symmetry S, we say that there is a disorder parameters with a parity even, and also for the odd case. So what I previously say that a system must have either an O1 order parameter or an O1 disorder parameter. The O1 just means that, first of all, the lower bound delta for the expected value uh, is some constant larger than zero. Also, the locality of the order and disorder parameters, L, is also some positive constant. And both of them are independent of both the system size and the separation between the order and disorder parameters. More concretely, our theorems are proved under the setting of gap ensemble. So the gap ensemble is just the counterpart of a gap system for the disorder phases. So here, by gap, that just means that if you consider all the ground states for different disorder realizations, for that specific realization omega, the Hamiltonian will also be uniformly gapped. So the gap of that Hamiltonian is lower bounded by some universal constant in symmetry sector. We will also require some symmetry conditions. First of all, we require that there's exact Z2 symmetries, meaning that for every realization of the system, the Hamiltonian will commute with the Ising symmetry. We will also require average translational symmetry, meaning that the probability distribution will be invariant under the translation. We will also require the disorder potential to be short range. This is just a very physical assumption, meaning that if two disorder potentials are very far away from each other, we shouldn't expect them to be correlated with each other. Just one important additional assumption that we are taking here, which is the phase homogeneity. This means that if you consider any two disorder realization omega and omega prime, the ground states associated to them are connected by a symmetric quasi-adiabatic continuation. So this just means that you can for any two disorder realizations, the two ground states will be in the same phase. So this naively makes sense because if you don't assume this, then we can just think up some weird examples where for this omega is disordered and for the omega prime is ordered, and this will just give both signals of the order and disorder parameters. Also, this will be a natural assumption if the omega is a continuous variable. So the disorder will indicate that we are now the disorder potential to be continuously curable. This is just because we already assume that all of the ground states will be gapped for different realizations. So as long as you can tune continuously between omega and omega prime, there just exists a quasi-adiabatic continuation between the two. So of course it will be in the same phase. So formally, our theorem states the following. We consider a gap ensemble satisfying the three requirements. First of all, the symmetry condition, and then the short-range disorder condition, and the phase homogeneity. The trade-off means the following three conditions. First of all, the existence, meaning that at least one of the order and disorder parameters will be O1 for the ensemble. We also show the mutual exclusivity, which means that the ensemble cannot have both, so you can only have one of them. We also show that just like in the pure case, we have a constraint on the endpoint parity, so any surviving disorder parameters will be parity even. So both endpoints will be even under the Ising symmetry. Let me briefly talk about the idea of this proof. So let's first talk about the proof intuition for the existence condition, meaning that there must be at least one of the order and disorder parameters. To understand this, let's first talk about the clean case. So in the clean case, you will just have a single symmetric gap Hamiltonian, and you will be able to consider the ground state for that gap Hamiltonian. And the idea is just that we can consider a restricted symmetry twist on some local region I. And you just consider the restricted symmetry action S on the region I, and you apply Si to the ground state to get another state omega prime. So we consider a buffer region just near the boundary of the twisted region I. So I is just this orange area, and the buffer region E is just the gray area near the boundary. And we consider the reduced density matrix of both omega and the twisted state omega prime on every region outside of the buffer region E. So both on the orange region and the regions that are very far away from the orange region. So intuitively, we know that if the system is disordered, then locally, even if you apply some restricted symmetry twist, you doesn't really do, or you don't really do anything to the system. So if you consider the reduced density matrix rho x and rho x prime, they should still be very close to each other. And on the other hand, you'll be able to see that if the system is ordered, then omega rho x and rho x prime should be very far away from each other. More concretely, we can consider two measures of the distance between rho x and rho x prime. First, dx is just the trace distance between rho x and rho x prime, and fx is just the fidelity between the two. So the colder the two states are, the smaller dx is and the larger fx is. So the first one, the graph inequality just tells us that since they both describe the same thing, there will be this trade-off between the two. So if dx is small, then fx is large. So this inequality tells us that uh, at least one of the dx and fx must be O1. So if, if dx is O1, is a O1 constant that's larger than 0, then we know that the symmetry twist will be detectable far away because you just apply some symmetry twist on the region I, and even if you are just measuring the system from regions away from the buffer region, you can still see a difference. So this just tells you that the system is non-range ordered. On the other hand, if fx is O1, so the fidelity is some positive constant, then notice that the fidelity can actually be written in this way from the Wuchermann's theorem. So this thing is actually exactly the disorder parameters that we consider. So Si is just the restricted symmetry action between the region E on the right and the region E on the left, and the UE is just the dressed operator on the endpoint of the symmetry operation. So by having an O1 fidelity, we know that the system will have a O1 disorder parameter. So this inequality will already tell you that either one of the following must be true. You must either have a non-range ordering or disorder parameter. After some more careful analysis in the clean case, you can actually show that the locality of the disorder parameter and the order parameter will also not be an issue. So we just go back to the original definition. I think this is a very important slide, and if you have any question, please feel free to ask. Okay. So let's move on to the dirty case. So unlike the clean case, in the dirty case, we cannot just focus on one specific state because there could be this possibility that some organization will be ordered, but other organizations will be disordered. So to consider these kind of situations, the key idea is just to estimate the probability of each case. So
Question.
sure.
I thought the assumption of phase homogeneity forbids this.
For what? Sorry.
The assumption of phase homogeneity requires either all realizations are ordered or disordered.
Oh, you're right. Sorry. I think yeah, you're right. But there could still be the possibility that the other parameters are different for different disorder organizations. So on average, it doesn't really contribute a lot. This is actually issue. Sorry, I made a mistake in making this slide.
I see.
So yeah, in the dirty case, there could be a issue that you have like very different disorder or other parameters, and they like on average you don't actually you're not actually able to find the OI and OJ with the non-zero with the one expectation value.
Mhm. So
Yeah,
even under the assumptions of phase homogeneity, this cannot be ruled out, and it takes some
yeah.
non-trivial work to rule it out.
Yeah. It's a non-trivial work to rule out, and it depends on
Mhm.
it relies on a probabilistic method to deal with this kind of issue.
I see.
Yeah. I Speaking of this part of the result, the existence of the existence part doesn't really depend on the homogeneity. It depends on a weaker version. So it's actually more general. But yeah, let's just focus on the homogeneity case here. Um, so the key idea of this part is just to estimate the probability of how of a state to be disordered. Um, what Another non-trivial situation that will happen in the disorder case is just that while the ensemble is translation invariant on average, each state is not guaranteed to be translation invariant. So in principle, there could also be a situation where on some part of the system you will be ordered and some parts of the system you will be disordered. So we can define two events, AI and BI, denoting whether a state will be locally ordered or locally disordered around a set time. More explicitly, we consider the set AI, the order-like event, to be the event where we consider the partition like this, where we have some region II just near the set I, and there's some buffer region on the right and left-hand side of the set I, and then the II prime, just the rest of the systems. The the event AI denotes a case where the mutual information between the region II and the region II prime is larger than some constant A. This constant is actually 1 over 32, but it doesn't really matter here, just some O1 constant. So we can see that denotes this corresponds to the case where the system will be ordered near set I because the fact that the mutual information between I and prime is large tells you that there exists some large coordinators between I and I prime, and this just gives you non-range ordery. On the other hand, we define the disorder-like events BI to be the case where the fidelity that we talked about on the last slide, or this like maximum overlap between omega and the twisted version of omega to be larger than some constant b. The constant b is also some O1 constant that's not important here. So as I described on the last slide, uh, if the event bi happens, then this tells you that the system will have a disorder parameter with the endpoint supported on II minus and II plus. So we know that the system must be disordered near set I. So what the clean case can tell us is just that if you apply the Van der Graaf inequality, we will be able to show that for each disorder realization, at least one of the event AI and the event BI must happen. So this tells you that the probability of AI and BI cannot both be too small because otherwise this will contradict this requirement. Another property that I want to emphasize here of the event AI and BI are that they are local events. So while the AI involves the mutual information between II and II prime, which is very far apart, you can just transform that, considering that the whole system is just a pure state. So you can actually show that the mutual information only depends on the reduced sensing matrix on this color region. So the AI is just some observable that only depends on the reduced density matrix on this omega I, which is the union of this color region. For the BI, it is the same because the U the UEI, where EI is just the I plus and I minus here, and the SII are all supported on this color region. So it also only depends on the reduced density matrix of the omega just on this region. So since both AI and BI are functions of the reduced state on the buffer window, we know that if you change the disorder that's very far outside of omega WI, this doesn't really change a lot of the expected values inside the buffer window. So it only changes AI and BI by exponentially small amount. So since changing disorder outside of the window doesn't really change AI and BI, we know that AI and BI only depend on the disorder near this window, and that's near the side time. So since the AI and BI only depends on the disorder just nearby, we know that if you consider two events, AI and JI, and they are very far apart from each other, the two events will be independent from each other.
Question.
Sure.
Suppose for the second point, suppose the region I'm changing disorder is extensively large. Uh, the this mutual information and the fidelity still only change by some exponentially small amount.
Yeah, exactly. So uh, the the reason this is true is just that um, the the be- the operation that you change the disorder outside of the region WI is just quasi-adiabatic evolution, and if the operation that you do is very far away from WI, you can just decompose the quasi-adiabatic evolution to some like three depths quantum circuit, and all of the contributions are very far away from WI will just be canceled with each other. This is just the trick that we did in our joint work on the CMI decay stuff. So uh, just everything will just cancel out with this stuff. The approximation error will only depend on the distance between the disorder that's changed and the region WI.
And here the key is that am I understanding correctly that you are using the phase homogeneity when you change the disorder so that there exists a quasi-adiabatic continuation?
Yeah, exactly. But there you can also assume the principle that local perturbations perturb locally, uh, which is not proven. But if you believe in that, you should also be able to see that AI and BI doesn't really depend on the perturbations far apart.
But suppose I change the perturbation far apart, but in an extensively large region such that the the two realizations belong to two different phases with respect to the Z2 symmetry, then I wouldn't expect the existence of a quasi-adiabatic continuation.
Yeah, you're right. In that case, I don't think we can like rigorously show that AI is not changed much.
Mhm.
So probably to show that rigorously, we will still need to assume the like phase homogeneity.
Thanks.
Yeah, thanks. So here's the proof sketch for the existence of either order or disorder parameters. The proof is done by contradiction. So we assume that there's no order parameters and no disorder parameters for the system. In this case, we can consider two distant events, AI and JI. So AI denotes the fact that the system is ordered near site I. JI denotes the fact that the system is ordered near site J. So if the system is ordered both near site I and site J, you can just cook up some order parameters, OI and OJ, on that. And the expected value between of the 2-point coordinators will be large. However, we already know that there's no order parameters, so the probability, so the case that the event AI and JI happen must be very small, so that if you take the disorder average, it doesn't really contribute a lot to the order parameter of the whole ensemble. And that means that the probability of both AI and AJ to happen will be very small. On the other hand, we also assume that AI and AJ are far apart. So as I talked about previously, they should be independent with each other. So the probability that AI and AJ both happens will be the uh, multiplication of the probability of each event to happen. Since the joint probability is very small, the probability of AI or AJ is also very small. Similarly, the same argument can be applicable to the disorder parameters, where we consider two distant events BI and BJ, each denoting that the system will be disordered near site I and site J. So we will require that the joint probability of the two events to be very small, so that this kind of locally disordered contribution will not be promoted to a global ensemble level disorder parameter. So this will give you another bound for the probability of the event BI and BJ. As I already told you, locally, the Fishwander graph inequality will tell you that at least one of the event AI or BI must happen. So this will tell you that the probability of AI and the probability of BI must add up to some constant larger than one. Otherwise, there could be a probability that none of them happens. So this will contradict to our previous estimation of the probability of AI and BI. So this gives you a contradiction so that we know that the ensemble must have either an O1 order parameter or an O1 disorder parameter. Let me move on to talk about the sketch of mutual exclusiveness. So this proof is still by contradiction. So we assume that the ensemble has both order and disorder parameters. So this tells you that there must be some renormalization omega, so that you have an order parameter on these two sides, and there will also be another disorder renormalization omega prime, where you have these disorder parameters denoted by the red line. So here again, we need to use the phase homogeneity. So uh, so that we know that for the states in the disorder renormalization omega and the states in the disorder renormalization omega prime, there exists a quasi-adiabatic continuation between the two. So if you apply the quasi-adiabatic continuation to one of the sets, for example, for the ordered state, this will conjugate on the order parameter and provide you order parameter for the states in the omega prime. So in this case, we arrive at both a disorder parameter for the state in omega prime and the order parameter for the state in omega prime. However, in the pure state case, we already know that this is impossible. Or if you consider one gap ground state, it cannot be both order or disorder. So this gives you a contradiction, and as a result, the order and disorder cannot exist within one gap ensemble. The proof that the endpoint parity must
Sorry,
be
sorry. One second. Hold on. Sorry, can you explain again? How did you go from the ensemble to how did you connect the disorder case with the translation event case?
um Yeah, here I'm lying a bit because the requirement that the gap state cannot carry order and disorder is not relying on the translation invariant case. So the idea here is just that I consider two state since the ensemble has both order and disorder parameters, there exist two state omega and omega prime. One have order parameter, one have disorder parameter. I can just apply a quasi-adiabatic evolution between the two, for example, on omega, so that I arrive at omega prime, where you have both a disorder parameter and an order parameter. Here, of course, omega prime is not, you don't need to assume that omega prime is a translational invariant state. But one thing you can notice is just that, um, for example, you can think, but you can actually show that this is still impossible as long as there's some intersection between this other parameter and the other parameter. The reason is just that you can think about the extremal case where, for example, the expectation value of the other parameter is one, this other parameter is also one, so that this red operator will stabilize the state, and the green operator will also stabilize the state. However, since the green operator will carry a parity odd endpoint, so the green operator will anti-commute with the red operator, so they cannot both stabilize one single state. This is the reason why this is actually still forbidden for
Oh,
the app state.
I see. I see. So this last result does not even rely on any ground state. It applies to any state.
Uh, well, the way I frame that it is, but the proof that like the proof that I just described assume that the red operator and the green operator are exact stabilizers of the state,
Ah,
but in general they are not. So in this case, you will still need to assume some like property of the state, and if you assume that there are ground states, you can just use HSP or related techniques to show that this argument still wins.
I see.
So
Thanks.
yeah, so we still need to assume the gap,
Mhm.
or you can assume SRE, which also work.
Mhm.
Yeah. So let's move on to talk about the endpoint parity of the system, where we show that the disorder parameter must have even parity. It's still by contradiction, where we can assume that the system have odd parity, and then we will have a disorder organization omega uh, with with a non-zero expectation value of this orange operator, and another say omega prime with also a non-zero expectation value. So by applying the quasi-adiabatic evolution, we will be able to arrive at a state in omega prime where you have like two disorder parameters with odd parity on different places. So our previous argument will still hold, and you can just cook up different projectors that anti-commute with each other, or you can just think of the case that in the pure state case, we know that uh, the state omega prime cannot have two odd strings living in the same gap spaces. So this just leads to a contradiction. And then we know that our assumption is false, and any surviving disorder parameters must have even endpoints. So let's do a quick recap of our main theorem. We show that the trade-off in the clean system will still survive in dirty systems. More explicitly, we consider the symmetric ensemble with short-range disorder and phase homogeneity. We show that there exists other parameter, and there exists only one parameter, and if the disorder parameter survives, it must have even endpoints. So let's move on to the real region effects of the system. So the region effects are very important in the context of disorder systems. It describes this kind of phenomenon where there could be a rare case where some large island, the uh, the small the small probability when it happens that all of the disorder just behaves in a certain way, so that locally it favors the opposite phase. For example, you can think of the case where outside of this rare island, the system is disordered. However, inside of this rare island, the disorder is just organized in a certain way that luckily all of the spin will just point downwards. And locally, if you look at it, it's still other phase. So the way I describe it already suggests that the region effect will happen very rarely because it needs a connective fluctuation of some OR local disorder variables. So we know that the probability of this kind of real islands to happen will just be exponentially small in terms of the system size, in terms of the size of the real islands. However, while all of these real region effects happens very rarely, it's actually very crucial in disorder systems. People have shown that it can give you some results beyond the perturbative estimation. It also connects the gap because, as you can imagine, in this orange region is one phase, and outside of the orange region is another phase. So you expect that uh, as a whole, the state will be gapped somehow. So the real effect is beyond what I previously described as a gap ensemble. So it's natural, and it's very important. So it's very natural to ask whether our results will survive, even if we consider the real effects. And that the actual answer is yes. We just need to generalize the notion of gap ensemble a bit to the notion of nearly gapped ensemble. So all of the requirements remains the same, except that we allow the existence of real regions. So previously we just considered the all of these different kind of gapped ground states. Now we allow the events that there could be a real region on region R, and the way we model the real region just to consider the it's just by local unitary. It's just by a large unitary acting on the region R. So this is just because outside of the region, we still expect the system to look locally like a gapped phase. So if you consider a state omega prime that only has real region inside of R, it should look locally the same as omega outside of the region. So you can actually prove that this kind of unitary representation of the region will exist. We'll
Uh,
also sorry.
yeah, I'm confused about one point. So in your previous setting, is this real region already included?
Yes.
Uh,
You
so
mean this one? Yes.
no, the previous one. Uh, Before this slide. Yeah, yeah. Is this effect already included in the previous discussion?
I you mean in the original
Yes.
theorem?
Yeah, yeah,
Yeah,
yeah.
I don't think so, right? Uh because in that case we will assume that the system to be gapped. But in this case, in principle, the state doesn't need to be gapped.
I see, I see. Mhm.
And probably I will need to emphasize that UR is just not a local unitary because R can be very large, and we don't require UR to have any structure inside of the real region. It could be very complicated, like scrambling unitary inside of the real region, and our results will still hold. So it's beyond the scope of our previous discussion. But one thing interesting about our modeling of the real region is just that there's if you consider any site I, the probability that you have a clean window near the site I will always be O1. So since the probability of a region happen will be exponentially small, so the event that the green region and the orange region to overlap with each other will also be bounded. So for any site I, there will also always be a finite probability that everything is safe inside near the site I, and you don't see any region near the site I. And we will call the event that this actually happens to be CI, which will be useful later. So let me just sketch the proof of the existence of either other disorder parameters under the presence of real regions. So the only additional ingredients for the proof is just that you would need to show that there's an O1 chance that each local event see no real. So again, by the Van der Graaf inequality, we will be able to see that the probability of AI, which means that the system is ordered near set high, is O1, or the probability of BI is O1, which means that uh, the system is locally disordered near the set high. Uh, our nearly gapped condition allows us to introduce an event of CI, which means that there's no region near set high, and we will also expect that the probability of CI will also be very large. So the idea of the proof will go the same way. So we will assume by contradiction that there's no order parameter and no disorder parameters, and we can consider two distant AI AJ, and we assume that there's no real region nearby, so that there's still a notion of order parameter near set high. So if
Question.
sure.
I think I have a basic question about the setup. So in the setup, are we assuming in most places there is translation symmetry?
I think in most, you mean in most realizations, disorder realizations, or like the ensemble as a whole, of course, has translational symmetry. But if you consider any disorder realization, they will not have a translational symmetry.
Then what does clean window mean?
A clean window just means that it doesn't really mean that there's no disorder inside. It just means that the disorder is not strong enough or weird enough that you have a real region inside. So the system still looks gapped
Oh,
near side time.
I see. So I can think of the clean window as a piece of the system that's in some sense short-range entangled, but the real region is a region where the system does not have to be short-range entangled.
Yeah, correct.
Mhm. I see. Thanks.
Thanks for helping me to clarify this. Yeah, so let me finish the proof. So we assume that there's no order parameter and no disorder parameters, so there exist, and we consider the two distant event AI and AJ so that the system is ordered near site I and site J. We also assume that there's no region nearby, so we assume that the event CI and CJ will also happen so that the system looks gapped or short-range entangled near site I and site J. So if all this event happens, we will be able to show that the system will be ordered near site I and site J, and you will be able to cook up some order parameters near site I and site J. And this will require that the whole collective probability to be very small, because otherwise it will give you another parameter of the whole system. On the other hand, since we can do the same thing for the disorder events, this will require you that the probability that BI and CI happens together will also be very small. However, since the probability of CI is very close to 1, so this being small already tells you that the probability of AI will also be small, and the probability of BI will also be small. However, originally we know that either PI is O1, PAI is O1, or PBI is O1, so this will contradict our original assumption. So this tells you that all of our previous proof will still holds, and the other disorder trade-off will survive the Griffith type revisions. So let's finish the talk by talking about the applications. I think I'm short on time. I will talk about how it's related to SPT and LSM and fermionic chains. So we know that the disorder parameter can actually serve as a very good probes for the SPTs. Explicitly, we can consider the Z2 times Z2 SPTs, and we know that if you consider the disorder parameter for each sublattice, for example, the product of the even sides or all sides, this will just gives you the string order parameters for the Z2 times Z2 SPT. We can But that was a clean case, and people actually don't have a rigorous foundation for considering the string order parameter for dirty SPTs. So uh, explicitly we consider the setting where you have an exact Z2 times Z2 symmetry, an average one-side translation, and because you have SPT, we also assume that there's no spontaneous symmetry breaking, meaning that you have an ensemble of SRE states. So since you have an ensemble of SRE states, there's no spontaneous symmetry breaking for either of the Z2 symmetries, or there's no other parameters for either of the Z2 symmetries. So you can just apply the theorem to both the Z2 on the even side and the Z2 on the all sides. And you will be able to show that since the other parameters are all vanishingly small, we know that the disorder parameters or the string order parameters will be an O1 constant. More explicitly, there exists the OI, OJ such that this expectation value is O1, and also on the even sides, you have similar stuff. Also, it's worth emphasizing that since our previous theorem considers the real region effect, so this still applies under real region effects. I will skip this part, but so we already know that for the SPD phases, the endpoint parity of the string order parameters will tell you information about the SPD classification. And for example, in a non-trivial Z2 times Z2 SPT, the OI for the even side will be odd, and the symmetry operations on the all sides and vice versa. And using the protocols that we talked about previously, we can actually show that this is also the case in the dirty systems. So in the dirty systems, the parity of OI on the green strings will be definite, will be the same as the parity of the OI prime on the green string. So basically the classification of the Z2 times Z2 dirty SPT is the same as the classification of the Z2 times Z2 clean SPT. Our theorem can also gives you an LCM for dirty systems. Here, the symmetry that we consider for the dirty system is just two symmetries with projective representations on each side. So we consider the Sx, that's a product of x on every side, and the Sz, that's a product of z on every side. So locally it's projective because the x anti-commutes. So we derive an LSM constraint telling you that if you have an ensemble that's symmetric and symmetric under both Sx and Sc, and there's no SSB under Sx or Sb, meaning that the ensemble is short-range entangled, then we know that the ensemble cannot be nearly gapped. So it must be gapless in a sense. So this is perfectly the error log for the LSM in disorder ensembles. The proof idea is just assume for contradiction that there could be an ensemble that's nearly gapped and satisfies this condition. Since there's no SSB, the tradeoff theorem will then force you to have a disorder string for each symmetry for both the Sx and Sc. The LSM obstruction just can just be proven by show that this is actually impossible. So the string orders for the Sx is not compatible for the string orders for Sc. I will sketch the proof briefly. So assume by contradiction that there's actually these string order parameters of x and the string order parameters of the z operators. So since our system have an average translational symmetry, if the z string have a non-trivial expectation value, we can just shift the z string by one side. So you start with the orange line in the middle, and you end up with the orange line in the bottom. So you can see that for the first orange line, the overlap between the orange line and the x strings, the green line, has four sides. On the other hand, after the translation, it only has three sides. But since on every side the z locally anti-commutes with x, so the X string either anti-commutes with the Z string or the Z string after the translation. So in the extreme case where all the three strings are stabilizers in every realizations, it just means that all of this U, V, and V prime stabilize the states, but U either anti-commutes with V or V prime, and this is impossible. So this gives you a contradiction, and you know that the system under this symmetry conditions cannot be nearly gapped. The final application is just the trade-off theorem for harmonic systems. So you can easily imagine that since we already have a trade-off theorem for spin systems, you can just do a Jordan-Weger transformation. So you start with order and disorder parameters for a spin system. After the Jordan-Weger transformation, you can actually show that the disorder parameters with parity even will just give you a bosonic endpoints. Well, we just give you a parity string with bosonic endpoints. So on every side, you will have Fi that correspond to the parity, and then on the endpoint there will be two bosonic operators. On the other hand, the other parameter under the Jordan-Weger transformation will just give you a parity string with harmonic endpoints. So our previous discussion about the spin system will just be translated to a trade-off theorem for the harmonic systems. So we know that the expectation value of these string order parameters must be O1. So in the case where we have the order parameter in the bosonic case, the after the Jordan-Weger transformation, O1 and OJ will be bosonic endpoints. And in the case where we have these other parameters, O and OJ will be harmonic endpoints. So on the fermion side, this will just correspond to the trivial phase and the phase of the Kitaev chain. And this will be the end of this talk. And the take-home message is just that the order and disorder parameters are very useful, and we can actually define the notion in the dirty systems, and we show that it still serves as a great probe for different kind of for the two symmetric and SSB phases in this ensemble. We can also apply that to different kind of settings, including SPT, LSM, and harmonic chains. Thank you so much.
Okay, Jimmy, thank you for the very interesting talk. Any other questions?
Hi. Yes, I have a question. So in the very beginning, you introduced that you have an assumption of phase homogeneity. I'm wondering, what does it mean by having this assumption? Do we have more constraint on the system setup?
The way I think about this is just that it's most natural if you just consider the case where the disorder strength is a continuous variable, and for all disorder strengths, the system remains gap. This will just ensures the phase homogeneity naturally.
For example, do we have an example where we do not have this phase homogeneity?
There could be weird examples. For example, if the disorder is not short-range coordinated, you can just consider the ensemble where you have two Hamiltonians. One is just in like two Hamiltonians of transverse field IC model, one with h smaller than j and one with h larger than j. In that case, you will have that. But if you are asking me if like requirement A and B are satisfied, whether we can derive C from A and B, then I don't know. I don't think.
I see.
I think in principle it could be possible because this sounds just like LPPL, but I think it's kind of hard.
I see. Thank you. And one more question. Can we generalize this picture to, for example, non-abelian groups, non-abelian symmetry?
Let me think about that. I think even in the pure case, this is not so clear whether it's generalizable.
Right.
I don't see any immediate obstruction because everything just relies on this inequality. So in principle, it should be doable. But yeah, I don't know of any existing literature about that.
Thank you.
I vaguely remember that Nevin has a master student whose thesis is about this, but it's not published, and I didn't check the result.
And can this be generalized to like anti-unitary symmetries and the symmetries not on-site symmetries that are not and internal symmetries that are not on-site?
Um, for symmetries that for anti-unitary symmetries, the issue is that it's very hard to define the restricted symmetry string. So I don't think that's very easy to do. For the for non-on-site symmetries, there are some technical difficulties. Um, I uh, I think it's mostly technical difficulties that cannot get around. It's like here you will need to consider gap ground states, and the fact that the symmetry factor rise is very important, so that all of our my previous argument, for example, like sorry. So this kind of argument, like when I assume that um, all the strings are stabilizers and you use the anti-commutation relationship to rule out stuff, this kind of stuff relies heavily on the fact that the symmetry is factorizable. But those are technical difficulties. I don't know whether you can get past that.
Mhm. Okay, any other questions?
Sorry, I have a question. So for fermion system, so every observable must have a fermion parity string, right?
Hmm.
You hear?
Yeah.
For example, can we have a Ci dagger Cj, such kind of observables? What does this kind of observable mean?
Oh, if it's Ci times Cj, then you know that when I and j are very far away from each other. If I recall correctly, this will just be mapped to these other parameters with parity odd, and then you will be able to see that the expression value will just vanish from our
So
result.
you mean if we have a exact fermion parity symmetry, then this kind of observable must vanish.
Uh-huh.
Is
You
that
vanish or exponentially small.
Yeah, it will be it will vanish when the distance between I and j goes to infinity. But yeah, it's exponentially small.
uh I see. Uh oh, okay. Thank you.
Thank you.
Yeah, that the expectation value of Ci dagger Cj is just the two-point correlation function of the operator C. The in the gap ground state is supposed to decay exponentially,
Yeah,
independent of whether there's translation symmetry.
I see.
Yeah, I mean
Yeah, and I think
this
you
is
can
proved
just
in the
derive
same
that.
paper. It's proved in the same paper for Hastings for the spin case.
I see.
Okay, any other questions?
So is your discussion restricted to 1D, or you can
Yeah,
get in some
yeah.
to 2D?
The ultimate goal is to generalize this to 2D, but you know the our techniques are mostly QI and probability series. The probability series part is completely fine. The QI part relies on the usage of the mutual information and or this trade-off between fidelity and trace distance. I I kind of remember that um, if you want to generalize it in this to 2D, you will need to assume some decay behavior of the mutual information and things like that. I guess uh, if you add that assumption, there could be a way of dealing with that, but yeah, I only thought about this briefly personally.
I
But
see.
without that assumption, it will not work. So the idea of order and disorder parameters is readily generalizable to two dimensions. The idea is just that for the order parameter, it's still the same. You just consider the two-point coordination function. For the disorder parameters, instead of a symmetry string, you would need to consider a symmetry disk. And then the dress operator would just be on the boundary of the symmetry disk. So naively, all of this result will still go through. It's just the technical difficulty.
In that case, what is the analog of even or odd endpoints for the JSON?
Uh, yeah, that's kind of hard. I don't think you can discuss that.
Mm-hmm.
Yeah, that part is not. I mean, in 1D, the fact that you can define the parity is not very important in the proof, though. So I don't think that will affect or not.
Mm-hmm. But the naive generalization seems to be in 1D, I'm looking at the zero dimensional endpoint, and I'm using the representation to label the endpoints. This is
Uh-huh.
really the characterization of a 0+1 dimensional SPT. Then perhaps for the 2D disorder disk, I should ask what kind of SPT I should put on the boundary of the disk. What kind of 1D SPT I should put.
I see. I see. Yeah, that makes sense. In that case, the the classification should be very complicated, at least more complicated, right?
The classification of the SPTs is still supposed to be something like the cohomology,
Yeah,
but
sure.
I
Yeah.
think the characterization based on the this kind of disorder parameter will be very complicated.
Yeah. I see. I see. That's very interesting, though.
And what did you say about the mutual information? What kind of assumption for mutual information do you need for that?
Yeah, this was a long time ago, so I don't quite remember. I vaguely remember that you need you 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 need the mutual information between the disk and the like complement outside of the buffer region to just decay exponentially small. So that's kind of like standard stuff, but it's not proven
It
without
didn't
like additional assumption.
didn't we prove it?
Um, we prove that with the additional assumption that the system the phase is described by some
Oh,
category theory that without with that I think we can say a lot of stuff, but without that I don't.
I see. Mhm. But that's something I think that's something that we should be comfortable to say, right?
Yeah, that's totally comfortable. I'm just saying that like from a totally mathematically rigorous perspective, it's still not proven.
Yeah.
Yeah, I believe it's true though.
Mm. Okay, any other questions? Okay, if not, I will represent everyone to thank you again, Jimmy, for the very interesting talk.
Thank you so much for having me.
Yeah, okay, bye.
Okay, see you.